Welcome to our online chemistry class. Our topic is aldehydes, ketones and carboxylic acid. Let us discuss the part number 3. In this part, we will discuss about the methods of preparation of carboxylic acid and physical properties of aldehydes, ketones and carboxylic acid. So let us discuss method of preparation of carboxylic acid. First method is from nitriles and amides. So nitrile means, or it is also known as cyanide. Functional group is dash C triple bond N, and amides is nothing but dash CO dash NH2. So alkyl or aryl nitrile on acid hydrolysis. Hydrolysis means addition of water. Acid hydrolysis means addition of water in presence of acid, H2 oblique H plus or H3O plus, gives first amide, which on further acid hydrolysis gives corresponding carboxylic acid. So let us discuss the reaction RCN. So functional group is dash C triple bond N. In that nitrogen is more electronegative than carbon. So carbon is electron deficient center of your nitrile or cyanide. And we add the water. So in water also we write H is the positive part, OH is the negative part. So negative part of OH, that is the nucleophilic part, get attached to electron deficient, that is electrophilic center of your cyanide, that is carbon. So OH is added to carbon and hydrogen is added to nitrogen. Triple bond gets converted to double. Okay, so what we get? RCOH double bond NH. This space is in which that one carbon contain two functional group OH and double bond with NH, that is imine. So it undergo conversion into stable form, and it is one of the type of tautomerization that we already discussed in ketoenol tautomerism. So only is the shifting of this OH hydrogen to NH. So OH bond undergo cleavage and it form a double bond with carbon. So C double bond O, and as carbon becomes pentavalent, the double bond of that carbon with nitrogen gets shifted to nitrogen, and nitrogen take that hydrogen. So R C double bond O NH2. So this is stable product. We can isolate this. Imine cannot be isolated. So our product is amide. Okay, and this amide undergo hydrolysis in presence of acid, that is acid hydrolysis. So we break the carbon nitrogen bond of that amide and we convert RCONH2 to RCOH. So simply again we see that this carbon is electron deficient center because it is attached with two electronegative atom, oxygen and nitrogen. So it is electron deficient. So OH will attack on this carbonyl carbon, and hydrogen gets added to NH2. So we get RCOH plus NH2 becomes NH3, and we get a carboxylic acid and ammonia. So this is the reaction, or you can shown directly 2 moles of H2O added to your cyanide in presence of dilute HCl. We can directly write down RCOH plus NH4Cl. So both way you can show the reaction, but when question is convert the amide into carboxylic acid, then you write the this second reaction, amide to carboxylic acid. So let us consider the example. So R is equal to CH3. If you write CH3, then your amide is CH3CO NH2 ethanamide. And how will you get this ethanamide? From this CH3C triple bond N. There are two carbon, so your nitrile is ethane nitrile, and alkyl group is CH3, so methyl cyanide is the name. CH3CN, CH3 methyl, and CN functional group cyanide. IUPAC name is the nitrile, 2 carbon ethane, and the compound is called as nitrile. So ethane nitrile gives CH3C single bond OH, double bond NH, imine of that ethane nitride, and here we get CH3CO NH2, that is ethanamine, ethanamide, and this ethanamide undergo hydrolysis in presence of acid gives CH3COOH, ethanoic acid, acetic acid plus ammonia. So you can write a reaction starting from your cyanide as well as from amide. So cyanide is methyl cyanide or ethane nitride, and amide is ethanamide, gives acetic acid as a product or ethanoic acid. If you have to prepare benzenamide, so what do we get? C6H5CONH2 on acid hydrolysis gives benzoic acid plus ammonia. Okay. Then next is from acyl chloride and anhydride. Acyl chloride functional group is dash COCl and anhydride dash COO dash CO dash. Okay. So acyl chloride RCOCl is the general representation. So what you have to write the change? You have to convert this Cl to OH. Remaining part is same. So RCOCl gets converted to RCOOH. So we have to replace this Cl by OH. So reaction is hydrolysis. So what do you get? RCOH plus HCl is the byproduct. So for example, R is equal to CH3. Name of the compound is acetyl chloride on hydrolysis in presence of acid H plus. Similar to your previous reaction, what do you get? CH3COH plus HCl, acetic acid plus HCl, and we can write the C2H5 COCl. This is the product C2H5 COH, that is propionic acid. Okay. Then acetic anhydride, if we take, then we can also prepare acetic acid. So again reaction is same. We have to carry out hydrolysis in presence of acid H2O in presence of H plus. What is acetic anhydride? CH3COO COCH3, that is acetic anhydride. React with water in presence of acid H plus. So we have to break. So OH will attach to any carbonyl carbon out of these two. So then we have to break this bond between this CO and O, and hydrogen is added to this O. So we get 2 moles of acetic acid. So general representation is, instead of CH3 there is R. So RCO twice O, or RCOO dash COR on acid hydrolysis means H2O in presence of H plus gives 2 molecules of carboxylic acid. So this is acetic anhydride, and all are familiar with this acid, acetic acid. It is also known as 2 carbon ethane, replace E by OH acid. So ethanoic acid. So your anhydride is ethanoic anhydride. Ethanoic anhydride. Okay. Then next reaction is third method of preparation is from ester. So all are familiar with the function group of ester, dash CO dash OR dash. Okay. So and general representation is RCOO R dash. This R and R dash may be same. Okay. We can use this R as H, but this R dash is not H. Okay, if R dash is equal to H, then it is not a ester, it becomes acid. But we can write this R is equal to H. then your HCOOR dash means ester of formic acid. So let us see the reaction. Acid hydrolysis of your ester. This ester on hydrolysis with mineral acid such as HCl or H2SO4 gives carboxylic acid and alcohol. So let us see the reaction. So here also you have to add water. Again OH is the negative part and carbon is electron deficient center. So OH will attach to C double bond O carbon, and we have to break this C double bond C single bond O. You can write like this. So we have to break. If we write the attack of OH, so we have to break this bond, and we can add OH to CO and H2O oxygen. So what do we get? RCO OH and R dash OH. So we get carboxylic acid and alcohol. Do not write, do not break the bond between R dash carbon and O. Okay, so OH will not attack on this oxygen. So always to break this bond, and we get this acid and alcohol, for example. So you can write reaction like this. This can be written like this, and I'll show the breaking of the bond between these two. So your OH will attack on this carbonyl carbon, and we have to break this bond between C carbonyl carbon and oxygen. So your byproduct is like this. Okay, or you can write here also. So in this way you can write the reaction. So to get CH3CO OH means acetic acid, and this one is C2H5OH ethyl alcohol. Here we get acetic acid means 2 carbon acid is ethanoic acid, ethyl alcohol means ethanol. Here C6H5CO C2H5, this group is ethyl, and C6H5COO means benzoate. So we get C2H5OH ethyl alcohol ethanol, and C6H5COOH means benzoic acid. Okay, so we replace this O C2H5 group by OH, not C2H5 by hydrogen. We get benzoic acid as your product. Remember this breaking of bond, it may be asked in your exam. So which bond undergo cleavage in multiple choice question, and reaction takes place in presence of dilute H2SO4. If it doesn't use dilute H2SO4 here, then reversible reaction can also be takes place, and your acid, which is a product, react with your byproduct alcohol to give ester back. So this reaction becomes reversible, and formation of ester is called as esterification. Higher, if we prepare higher esters of fatty acid, then the reaction is esterification. Okay, so this is about the reaction. To avoid that reversible reaction, we use this acids. Okay, and in that case, got to use concentrated esters. So that we will discuss in the chemical properties under the heading of formation of ester or esterification. So I'll write here box. Okay, so in this way you can write the back. Then next reaction is preparation of again your acid, but by alkaline hydrolysis of that esters. So esters heated with dilute alkali like NaOH or KOH, sodium hydroxide or potassium hydroxide, it forms water soluble sodium or potassium salt of that corresponding carboxylic acid, and that salt undergo hydrolysis in presence of concentrated HCl gives corresponding carboxylic acid. And alcohol or phenol, it is aromatic in nature. So let us see the reaction. Your ester RCOO R dash. So C2H5COH, 2 carbon here and 1 carbon here means 3 carbon acid is obtained, and 3 carbon acid is propanoic acid. So here it is the word replace OIC acid by the word OAT, and your alkyl group is CH3. So CH3 means methyl. So name of this is methyl propanoate or methyl propionate. 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 That is common name. So it react with your ester, react with dilute NaOH. So this CH3 and that OH gives CH3OH. So we'll write the attack. This ONA, sorry, Na is the positive part, OH is the negative part. So OH will attack on carbonyl carbon. Okay, so you can write OH will attack on carbonyl carbon. Like this. OH will attack on carbonyl carbon, and the carbonyl carbon oxygen bond undergo cleavage, and it will form O minus, that will abstract the hydrogen, Na, which is the positive part here. Okay, so that O minus will take Na plus. So do it C2H5COO Na and CH3OH. We get methyl alcohol or methanol. So sodium propanoate react with dilute NaOH gives, sorry, methyl propanoate react with dilute NaOH gives sodium propanoate, plus methyl alcohol. And if we carried out the acid hydrolysis of that sodium salt of propaneic acid or sodium propanoate, then what we get is O minus, we will take H and we get C2H5COH, Na react with OH gives NaOH. So we get propanoic acid and NaOH. So sodium or potassium salt of higher fatty acid, that is known as soap. Hence the alkaline hydrolysis of ester is also known as saponification, formation of soap. So saponification, it mainly contains higher number of carbon atom in your alkyl group, then it is called as that fatty acid, and the sodium or potassium salt of higher fatty acid is known as soap. Okay, then next is from alkene by oxidation reaction. So C6H5 CH double bond CH2 means phenyl ethene. Hydrogen of ethene get replaced by phenyl group. It undergo oxidation. Oxidizing agent is KMnO4 in presence of dilute H2SO4. So we have to oxidize the carbon-carbon double bond. So C6H5 COOH, and this CH2 gets converted into CO2 plus H2O. CO2 plus H2O. So you can write that byproduct here along with your main product as H2O. Okay, the byproduct is H2O. So this you can write the byproduct. In this case, in cyclohexene, only one double bond is present, so it is not a benzene. So cyclohexene on oxidation with KMnO4 and dilute H2SO4, it gives, we have to break the carbon-carbon double bond and we attach COH group. So that C gets converted to COH. Okay, so you can write a reaction between KMnO4 and dilute H2SO4 that gives a nascent oxygen, and that is used for the oxidation purpose. So this is acidified KMnO4, which is used as an oxidizing agent. Okay, so this is about the reaction. Here one more product is CO2. Okay, so CO2 is also one of the byproduct. Then next reaction is from dry ice. Dry ice means solid carbon dioxide and Grignard reagent. Grignard reagent is alkyl magnesium halide, that is Grignard reagent. So when your Grignard reagent RMgx react with solid carbon dioxide, so in Grignard reagent, which is the negative part? Alkyl group is the negative part, so we add the negative sign to this. carbon and positive sign to MgX. Okay, so which is the negative part of the Grignard region? It is R. So now I write the reaction how this Grignard region will attack on the carbon dioxide, that is dry ice. So this alkyl, which is the nucleophilic part, will get attack on electron deficient center of your reagent, that is oxygen, because electron deficient, that is carbon, because oxygen is more electronegative and carbon is less electronegative. So it will attack on carbon. Okay, so R minus will attack on carbon. Then this bond between oxygen and the bond between oxygen and the bond between oxygen and carbon get shifted to oxygen, and oxygen become minus, that will take the MgX. So MgXO here, and R will attach to carbonyl carbon. So RCOO minus MgX plus. Okay, so that is a complex, it is unstable. Then it will go hydrolysis, and we have to break bond between oxygen and Mg. So here we write the breaking of bond between oxygen and Mg. So in this way we have to break the bond, and as oxygen more electronegative than magnesium, it take the hydrogen, so we get RCOH, and MgX react with OH, so get MgXOH. Okay, so what we get, and this addition of water takes place in presence of acid, so it is acid hydrolysis. So I'll again explain. Alkyl magnesium halide react with dry ice or solid carbon dioxide in presence of dry ether, gives a complex, magnesium complex, which is unstable, and that magnesium complex of corresponding acid react with acid hydrolysis. That means react with water in presence of acid gives RCOH plus MgXOH. So we take carboxylic acid from alkyl magnesium halide. So if R is equal to CH3, then here we get CH3 COO Mg NaX ClBrI, and here we get CH3 COH. So if we take methyl magnesium halide, your product is CH3 COH, methanoic acid, acetic acid. If we take ethyl magnesium halide, here C2H5 COO MgX. So what do we get here? C2H5 COH, means propionic acid or propanoic acid. Okay, so in this way you can prepare the acid, but remember that here in your alkyl halide, if it is one carbon, in your acid there are two carbon, because we added one carbon from your solid carbon dioxide. So number of carbon atom increase by 1 unit to your alkyl group. So how many carbon carboxylic acid you have to keep. According that you have to select the alkyl group and it is added to carbon dioxide. So this is about the reaction from dry ice, solid carbon dioxide and Grignard reaction. So then physical properties of aldehydes and ketone. So let us discuss the nature of this carbonyl group C double bond O. As I already said that carbon is electron deficient, so it carrying delta positive charge. Oxygen is carrying delta negative charge because oxygen is more electronegative than carbon. So this carbonyl group is polar group and it is due to the polar covalent bond, and due to that if this group come in contact with another carbonyl group of that aldehyde ketone compounds or carboxylic acid, then there is an interaction and that interaction is called as dipole-dipole interaction because there are two poles, positive and negative poles. Such a type of interaction is called as dipole-dipole interaction or attraction. And due to this dipole-dipole interaction, some properties are shown by these compounds. So physical state and boiling point of these aldehydes and ketone. So formaldehyde, the first member HCHO, it is gaseous in nature at room temperature, having irritating odor. Then acetaldehyde is extremely volatile. Acetaldehyde means CH3CHO, volatile, colorless. Extremely volatile means those compounds which have low boiling point, they get easily evaporate. So for example, petrol, diesel, these are the volatile liquids. So it is extremely volatile, colorless liquids, and higher aldehydes having pleasant odor or smell. Then acetone is also a liquid at room temperature. So acetone, all are familiar with the dimethyl ketone CH3COCH3 having pleasant odor, and the remaining higher ketones also have bland odor. Then boiling point of any compounds, here we consider the aldehydes and ketone, increases with increasing the molecular mass. So this is the general statement for all boiling. If we increase the molecular mass of that corresponding class, then boiling point increases. But there are some criteria also, branching, non-branching. The next one is solubility of aldehydes and ketones. Lower members of the aldehydes and ketones are soluble in water due to formation of intermolecular hydrogen bonding between carbonyl oxygen and hydrogen of water molecule. So here that hydrogen bonding is shown. Similar type of hydrogen bonding is shown in your answer while writing the answer of the questions. Okay, so you have to mention the delta positive charge over carbon, delta negative charge over this oxygen. As this oxygen in water is more electronegative, it carrying delta negative charge, and these two hydrogens carrying delta positive charge. So hydrogen of that water get attracted towards the oxygen of carbonyl group, and that interaction is called as intermolecular hydrogen bonding because hydrogen is involved in this bonding. Then solubility decreases with increasing the molecular mass because hydrocarbon part increases, hence cannot form hydrogen bonding. So if the bulkier group means alkyl group, hydrocarbon group get attached to this carbonyl carbon, that decreases the solubility because if we increase the alkyl group, number of that carbon and hydrogen goes on increasing, that increases the molecular mass and hence solubility decreases. Then polarity of carbonyl group. So as I earlier discussed that in your carbonyl carbon, carbon is less electronegative than oxygen. So carbon carrying delta positive charge, oxygen carrying delta negative charge. So flow of the electron between carbon oxygen covalent bond get shifted towards the oxygen, so towards the more polar or more negative pole oxygen. So that bond is polar in nature, and that carbonyl carbon becomes delta positively charged, means it is electron deficient. Oxygen becomes electron rich, so that carbon acts as a electron deficient center, that means electrophile, and hence it is easily attacked by the electron rich reagent, that is a nucleophile. Okay, so here the resonance structure can be shown, and the combination of these two structures is the resonance hybrid, and that's why the attack of nucleophile can take place on carbonyl carbon. So as we already discussed during the method of preparation of your carboxylic acid, I have shown the some reaction with respect to this, in that nucleophile will attack in esterification, preparation of different acids from esters. Okay, then physical properties, boiling point and solubility of carboxylic acid. Lower aliphatic carboxylic acid up to 9 carbon, first 9 members are liquid with irritating odor, and higher members from carbon number 10 are colorless, odorless, waxy solids. Then second one is they have higher boiling point than corresponding alkanes, ethers, alkanes carbon carbon single bond, ethers CO dash C means ethers, alcohols means dash OH, aldehydes means CHO, and ketone means COH. Sorry, C double bond O dash. So what is the reason behind that? Why the boiling point of these carboxylic acids are higher? The reason is that your molecules of that carboxylic acid, two molecules combine together and they form a dimer as shown in this diagram. This is one molecule CH3COOH. This is first molecule of your acetic acid, and this is the second molecule CH3COOH. This is the second molecule of your acetic acid. So oxygen of first acetic acid and hydrogen from OH group of second acetic acid molecule, they get attract and they form intermolecular hydrogen bonding, or hydrogen of OH group of first acetic acid molecule and CO oxygen, carbonyl oxygen of second acetic acid molecule, they form intermolecular hydrogen bond, and due to this intermolecular hydrogen bonding between two acetic acid molecule, it forms dimer. Di means two. Those two molecules get combined together, and due to that we require more energy to break the bond along with the another bond and convert that liquid into gas state. So boiling point due to this dimerization, and this dimerization is due to intermolecular hydrogen bonding, its boiling point increases. Such type of dimerization is not possible in case of alkane, ethanes, alcohols, aldehydes and ketone. Even though your alcohol contain hydrogen bonding, but not such a dimerization, and that's why the boiling point of your carboxylic acid is greater than that of alcohol also. Then lower aliphatic carboxylic acid up to 4 carbons are miscible, means soluble in water. So all are familiar with that, acetic acid is soluble in water, and reason is behind the intermolecular hydrogen bonding. So instead of the second molecule of acetic acid, if you write water, that hydrogen of OH H2 get attracted towards this carbonyl oxygen and they form intermolecular hydrogen bonding. So when question is related to solubility, then one molecule of acetic acid and one molecule of that water, you have to write and write down the hydrogen bonding. So it is written while discussing the previous this one. So this is the solubility of simply here write down R group and here OH, or you can write R as a CH3. So this is regarding this hydrogen bonding is shown when you explain the solubility of aldehyd, ketones and carboxylic acid. Okay, remember that. And when you have to show the you have to explain the higher boiling point of the carboxylic acid, then you have to show the dimerization of this acetic acid. Okay, then due to this intermolecular hydrogen bonding, solubility of carboxylic acid increases, and the solubility of carboxylic acid decreases with increasing molar mass. This is the general statement. Aromatic acids, means benzoic acid, are insoluble in water at room temperature. Then next one is the, here we can check the diagram of your boiling points chart. In the chart, formic acid, that is methanoic acid, boiling point is 373, and as we add CH2 group to this, the molar mass increases, the boiling point also increases. With increasing molar mass, boiling point increases. So number of carbon atom and hydrogen increases, boiling point increases. Then compound, family, molar mass and boiling point, and here we can check the corresponding molar mass of these different compounds. Nearly same molar mass, their boiling point is different. So alkane, ether, they do not show intermolecular hydrogen bonding, so they have lowest boiling point. As compared to aldehyde and ketone, there is a strong intermolecular hydrogen bonding in alcohol, because that carbon oxygen bond is present in aldehyde group, but in alcohol dash OH is the functional group, so alcohol have much more stronger intermolecular hydrogen bonding, so alcohol have higher boiling point than the aldehyde and ketone also. And in case of carboxylic acid, there is a dimerization along with intermolecular hydrogen bonding, so carboxylic acid, here acetic acid, has higher boiling point than the corresponding alcohol, that is N-propyl alcohol, having nearly same molecular mass. So the reason behind it is the intermolecular hydrogen bonding and dimerization in the carboxylic acid. That reason explain the higher boiling point of carboxylic acid than the corresponding alkanes, ethers, aldehydes, ketones, and even though alcohol also. So this is about the physical property. Thank you very much.